Am I audible? Okay. So today we are going to see another topic. That's game playing. You might know that artificial intelligence is having various applications in real life. So in game playing also this artificial intelligence is playing a huge role. So in different kinds of games it is involved, and how it is involved we will see some techniques we will see here. So in game playing basically the uh, games are well defined problems that are generally interpreted as requiring intelligence to play well. So a game consists of set of two or more players. Then the players will give their moves, and there will be some specific kind of strategies involved for the moves taken by the players. So this kind of uh, moves or the strategies involved in game playing is uh, used in such a way in artificial intelligence that there are certain algorithms or rules which will give the provision for game playing. So there are different types of games in AI. There will be perfect information and imperfect information. So what is perfect information? It's uh, it's a kind of information where all the relevant information is available to the decision makers without any ambiguity or uncertainty. Every possible outcome and its associated possibilities are already known. So that will be the perfect information available. And the imperfect information will be the decision makers when uh, the information is incomplete or inaccurate about potential outcomes or other relevant factors. And the accessibility is the extent to which information is available and can be utilized by decision makers, and how effectively individuals or systems can make informed choices based on information at hand. Based on that, the types of information available, which will be the uh, applied in various games. In for perfect information, we have some games like chess, checkers, Go, Othello, and for imperfect information are battleships, blind, tic-tac-toe. So these are some of the games involved where these kind of strategies are used and the information are used for playing. And along with that, deterministic and chances of moves. So two different types of classification are there where the games are divided. So in chance moves, backgammon, Monopoly have the perfect information, whereas bridge, poker, Scrabble, nuclear war have imperfect information. These are some of the games based on the chance of moves. The deterministic games, as you already know, that these games already you might have heard about these games or played before. So these games involve the outcome of each move is completely determined by player's choice, and there will be no element of randomness. Whereas in chance move games, the element of randomness is present in which outcome of a player's move may be influenced by chance events, uh, which occurs through dice rolls card draws, etc. So uncertainty is present in these kind of games. So based on that, these games are designed. Next, we'll see game tree. So tree and graph you have already learned in previous classes. So here, game tree is involved in such kind of games where there will be the game which will be in the form of layer tree. The nodes of the tree are the game states, and edges of the tree are the moves by the players. So this you have the root and child 1, child 2, and it will have the leaf node, leaf 1, leaf 2, leaf 3, and up to leaf n. So in such a way, the game is strategically designed through which a player uh, do his moves at, and at each alternating level, one player makes the choice. So two players will be there in the examples which I have shown you in the previous slide. In that games, so two players can have the choices. One player will be having uh, can be we can say that it will be max and min. So what is the max? So the max is divided, max and min are divided into layers where the one player will first start his move and next the second player means its opponent will uh, give his own move. So it will give counter moves to by each of the player in a game. And the leaves of the game are labeled with the outcome of the game and their game ends. So at last we will see how the best possible path we can determine in a game. So there are some algorithms which will help us to determine that. We will see in the later parts. Moving on to the example of tic-tac-toe game. So here it involves max and min, what I have already told you. The two players are playing that game. And the objective is to write a computer program in such a way that computer wins most of the time. So here just we are seeing the example. We'll see the algorithm involved later. And here you can see here the first state is there where the max is player 1 max is taking his move. Then it will give up to 9 different kind of moves which will be uh, further given by the player min, and it will be divided again into different parts, and again one move will be divided into different parts. Like that it will be divided till we reach up the end. And here we have the utility as -1 0 or +1. So -1 will be game is uh, won by min, and 0 means draw, +1 means match won by max. So there also three approaches are involved in the gameplay, which increases in complexity, use of generalization, clarity of their knowledge, extensibility of their approach. So complexity is the simplest approach, relies on predefined rules or moves without generalization. And use of generalization is the minimal or no generalization, where each move is based on a fixed rule for specific scenarios. The clarity of the knowledge is the clear but limited knowledge of strategy. list of if-then instructions that don't adapt or generalize beyond the predefined moves. Then extensibility is the hard to extend only works for defined situations. New situation requires addition of new rules, making it inflexible. So these are the approaches which to keep in mind in a gameplay. Then here you can see that max x and max mean 0 I have told you. So these players will have their turn, alternate turn one after another. So the max x will try to maximize score by making moves that increase chances of winning, whereas min 0 tries to minimize score by making moves to reduce max chances of winning. So it it will counter the moves of the max, whatever max has taken its move. Uh, Next is the adversarial search. So it's a search algorithm for finding an item with specified properties among a collection of items. The items may be stored individually as records in a database or may be elements of a search space defined by a mathematical formula or procedure. So this algorithm will look into uh, briefly what are the different techniques or algorithms are used in this algorithm. So it is involved in game playing and it relates to competitive environment where in which the agent goals are in conflict, giving rise to adversarial search. This we have already uh, seen in the last two slides how two players are competing with each other. There's an assumption an aim is present where two agents, uh, the actions are alternate to each other. When utility move values for each agent are opposite of the other, which creates adversarial situations and the fully observable environments are there. So we have seen that in the last slide, that -1, 0, and +1 are the different utility values we have seen, uh, which will give rise when the two players are playing a game. And the applications in game playing is basically uh, so this things have to be kept in mind while using this search algorithm. So firstly, it should be a two-player game. Then the players uh, have to give their alternate moves. Then both should have perfect information. So without information, that moves cannot be decided. And the dice, using of dice is not involved here. And the clear rules for legal moves should be there and the outcomes should be well defined. So we must have the outcomes for the game playing using the algorithm. That we'll see how the techniques can be used to determine the outcomes. So the adversarial elements, these will be involved while writing our algorithm and determining the moves and the result. So initial state SO is how the game is set up at the start. Then operators or players define which player has the turn. Then actions returns the set of legal moves in a state and the result, which is the result of moves in the state space. And the terminal test determines when the game is over. The state where the game ends is called terminal states. This you can see in this diagram. Two players I have already told you are involved, which will give their counter moves one after another. Then the terminal node will decide that the game is ended. So win, loss, or draw will be given by these utility values. So the min max or minimax, you can see when it's written minimax. Minimax, we can say minimax algorithm and alpha beta pruning are the two adversarial search algorithms used. So these two we learned here. Now moving on to the first algorithm is Minimax algorithm. So what is Minimax algorithm? Uh, as we are dealing with the gameplay, so it is used in the two-player based games only. And it is an algorithm that is used to find optimal moves for the player, assuming that the opponent plays optimally. When the two players are involved, main and max, the maximizer tries to get the highest score possible, while the minimizer tries to get the lowest score possible. So one will get uh, to the highest score, and one will get the another player is not getting the highest score. So the counter moves will be there, and this we can represent with the tree. It will start with the root node, and the two space it will move, and again it will have the two nodes. So two like that. The moves will be divided, and finally it will end at the terminal node. So these kind of values are already predefined. So based on that, we will find how the optimal path we can determine from using the Minimax algorithm. This we will see. These values are already defined here, so no need to take another values. So here these are already defined to you. So this is the step how Minimax algorithm can be used. And see from here it will start and it will end at the terminal values. Then we have to compute the utility of each node bottom up from leaves towards node. From here it will be started towards the root node. Here the final value will be put. And after that we will determine what is the path involved, how we have determined this, how we have found the root node value. Then at each max node, select the node with maximum utility. So from name only, you can uh, guess that it will be the max value only, and minimizer will be the mean value only. Based on the two values, here -1, 4. So which is the max value we can put here? It will be your 4. So like that, we will put. We will see in the next slides. And when the root node is reached, the optimal move is determined. So optimal value we can determine after the value is put in the root node. Here we have taken one example. I will just share with you. Just a minute. Just a minute, I'm sharing. we were able to see. Here I have taken one example. This is a different example. You can see. I'll tell you what are the values I have written. So first we will be given this terminal values only. Based upon that, we will determine the whole tree. Here the root node value we will find out at the last, and from that the most convenient path we will determine. So, here you just see here max, then mean, then max. So these players are giving their moves. First it is started by max at root, then mean. In alternate way it will go on till the terminal node is reached. So in min-max algorithm, directly with DFS we will apply. We will move towards left nodes. As we have already learned about DFS, I will not go into depth. So just we are using here the DFS method. First, here these values will not be there. It will be blank like this tree. Only these last values will be there. Based upon that, we will determine the values of the other nodes. We'll start with the root. Here no value is there, no value. We'll move on towards left until we reach this value, 10. We have reached this value, which is present at the extreme left hand side of the tree. Then from here, we will backtrack and put the value 10 here. We will write, not we will write in this box, we will write in the side here. Then again we will look whether we have to take the max value. Here we have to take the max value. Here we have to take the mean. Here we have to take the max. So upon comparing these two values, here we will write 10. Then again it has one child towards the right hand side. Again we will move towards that. Here it's 9. So between 10 and 9, which is the max value? 10. So directly we will put here 10. So value of this node is 10. Then we will again push it towards this node. Since it's already empty. So we will just put value and we will again backtrack towards the root. Like this it works. Then here again we will see. Here we will write 10. Then again we will move towards this node, towards left hand side, and finally we will reach this node which is giving the value 14, and this we will push towards this node which is already empty. We'll write 14 here. Again we will go towards this right hand side of this node. Here the value is 18. Upon comparing 14 and 18, the max will be 18, so we'll write 18 here. The value will be written here, and we will eliminate the 14 from here. So 18 will be present here, which is moved towards this parent node. We'll write 18 here, but since it's mean, we have already written 10. And 18 is just pushed towards it. 10 and 18 upon comparing, so minimum value we have to write, which is 10. We will write here 10. So 18 will just got eliminated. Then again we will backtrack towards the root node. It's already empty. So 10 we will write here. Then this part is complete. We have completely traversed this part. Now we will traverse towards right. Again we will go here, it's already empty. Again towards left we will go. Again here it's empty. Again we will move towards left. So 5 is there. So 5 we can again backtrack here. We will write 5 here. It will be empty. Again we will move towards this side. 4 is there. So 4 we will be backtrack and push towards it. So between 5 and 4, which is the max value 5. So we will write in this node 5. Again this will be pushed and backtrack towards this parent node 5. We will write here. So this side is now completed. We will move towards this side. Here we will go. Here the node is empty, so we will move towards left. We have found 50 here, which will be pushed towards the parent node. We will backtrack. Then 50 we will write here. Then again we will move towards right. Here 3 is there, so it will be pushed towards it, and between 50 and 3, 50 is max, so we will put the max value here. 3 is just, we will not write, it will be discarded. Again 50 will be pushed towards right. 5 is already written there, 50 and 5, so comparing these two, mean will be 5. We'll write here 5. Again we will move towards root, and here 10 is present, so between 10 and 5, max value is 10. So we will write 10 in the root now. Whoever's mic is on, just switch it off now. Switch off your mic. Bornil, can you hear me? Can you switch off your mic? Bornil, can you switch off your mic? Okay, so anyways, we will get this tree with these values. So each node is having this value. So now we will see which will be the most convenient path here. So here it's written 10. Then again in this node it's written 10. Then again 10, and at last 10. So most of the uh, nodes are having value 10. So this will be the most convenient path here. We can write this tree, just you all see once. We'll see another example after that. Hope you can get the idea how minimax algorithm we can apply. Now we will see one another example here. I have written only one tree. So like this, you will get the problem. We will try to solve this. So we'll start from here. Then we'll move to this node, then this, then this. We are using the DFS technique. So we'll move towards the extreme left of this tree. It's 10 is 10 is present here. So 10 will be again pushed towards it. We'll write 10 here and we'll move towards this side. So 11 is present. This will be pushed here. So max, mean, max, we can write this symbol. Any symbol can be used. So don't go away with that. That this symbol is only used for max. So any symbol can be used. It will be written as min max. If it starts with max, then alternatively it will be mean, again max, again mean, and it will be terminated here. So here it's mean. So mean value will be 10. So we'll just eliminate this. So now it will move towards it. So we're starting like this. Then here we have found one another node. So we'll move towards it. Just we will write 10 here. Again we will move towards it. Here 9 is present. So it will backtrack, push towards it, 9. So here again we have to take the mean value. So here going towards it, 12 is present, so it is pushed. So we are writing the mean value between 9 and 12, 9. Then again it is pushed towards it. So max is present, so max value between 10 and 9 will be 10. So we'll write 10 here. It will be again pushed backwards towards this parent node. So if there is no node, then we have to directly push it towards it. And again, we will move towards the remaining nodes. Here's the value is not present. We are pushing the 10 towards it. Then we are going towards this direction. No value, no value. Then reached 14. This will be backtracked and pushed 14. Then again move towards this side. 15 is there, so push back side. So mean value will be 14. We'll write 14 here. It will be pushed towards it. 14. Now again going towards this side. This side 13 is present. We'll push towards this. 13 we are writing. Then again towards this side we will go 14. Then again mean value 14 and 13 will be 13. We'll write 13 here. This will be pushed towards this side. Max will be 14, so writing 14. This will be pushed towards here. Here mean with 10 and 14, so 10 will be written here. then it will be pushed towards here, 10. Then we are again going towards this, and this, then this, between 5 and 2. Between 5 and 2, then it's move towards this 5 and 2. Min is 2, so 2 we will write here. Then again 2 is pushed towards this 2. Then this side we will move this side. So 4 is there, 4 will go here. Again this side we are moving. 1 is there, 1 is pushed here. Minimum is 1. So 1 we will write. It will be pushed towards this. So max between 2 and 1 is 2. 2 we will write. It will be pushed towards this side 2. Again this side. Three is there. We'll write 3 here. On this side. 22 is there. 22 we'll write here. Mean value is 3. We'll write 3. And it will be pushed towards this. And it will go like this. It's now reached 20. So it will be pushed 20. We'll write here. Go towards this side. 21. It will be pushed 21. Mean value is 20. So now it will be pushed 3 and 20. 20 is max, so we will write 20 here. It will be pushed 2 and 20. 2 is minimum, we will write 2 here. And it will be pushed 10 and 2 is 10 max, so 10 we will write here. So finally we will get this result using the Minimax algorithm for this tree. Now you can get the better understanding with the 2 examples I have used. In this way we can use the Minimax algorithm. So we are using DFS directly, we will moving towards the left. So here also the optimal path is this side only. Here we are getting all the nodes as 10. Okay. Now we will move on to another algorithm, that is alpha beta pruning. So it is just like your Minimax algorithm, but it's slightly different, not exactly same. It will use DFS also, but it's slightly different. How it's different, we will see with an example. Just the slide, what are the terms we are using. So it is a way of finding the optimal Minimax solution by reducing the number of nodes that need to be evaluated by only considering nodes that may be reached in gameplay. And the alpha beta pruning, the 2 terms you will come to know, alpha and beta. Alpha is the best already explored option along path to the root for maximizer, and beta is the best already explored option along path to the root for minimizer. So just like the Minimax algorithm, here we will use min max term only. So alpha will give you the max term, and the beta will give you the mean term. How it will give, we will see with an example. Here for max, we are just writing alpha as minus infinity and beta as plus infinity. This we can write, but directly also we can write that. I will explain with an example. So just go through it once. So it is the method how we are using alpha beta pruning. We will define the alpha and beta value, then compute the utility of each node bottom up from leaves. We'll also start from this bottom level towards the node. Then at each max node, select the move with maximum utility. So the alpha and beta values we have to identify. If we are getting max value, then we'll be using the alpha value, and if we are getting the mean value, we will be using the beta value. And alpha will be greater than equal to beta value. And when the root is reached, then the optimal move is determined here. Then this is the rules how we can identify. I will explain with a simple example. Here I will not use the alpha equal minus infinity or plus infinity. That I will share with you later. One example. This I will just show you just one simple example. How we can determine how the pruning is done. Pruning means uh, if we are getting any value not matching with our uh, already determined mean or max node. So there how we can put, so that we have to determine if if the mean or max is not matched. So then we will discard one side of the branch of the tree, that is called pruning. Means the alpha will be greater than or equal to beta value only. That condition we have to satisfy. So I will just share with you one example. Just see how alpha beta pruning can be used. Here we are looking into another example of alpha beta pruning. Likewise, we will see one another example that I will share with you. Just see this simple example now. So just like the minimax algorithm, it will start with the node A. So it will be max as the player is taking its first move is max, then mean, then max, and then the terminal is reached. These have these values, and the other nodes will not be having this value. Just like this tree only, it will be there, and these values will be there. So how it is applied, we'll see. Just like minimax, it will start from root node. It will move towards left side till it reaches the leaf node. This side it is 1. So it is -1, and again it will move towards here. It will be backtrack 1 -1. and again it will move towards right hand side where it is 4 there. 4 will be pushed towards it, and since it is max, so we will put the max value, which is 4. 4 we will write here. Again it will push towards it. It will be backtracked towards its parent node, and this parent node is empty, so we will directly push 4 towards it. We will not write 4 here, we will update 4 afterwards. We'll just see 4 will write. Then this side we have another branch attached, so here one node is there, it is also empty. Then we will traverse towards this side, we will go, and here 6 is present, so it will be pushed towards it. And as you have already know that the max will be alpha and mean will be beta. So what it's present here, here it's max, and here we are writing 4, so it will be mean. So what we can determine from this, that the value will be less than 4. So here will be 4 only, and here it will not, it will be max 6. So value should be 6, not less than 6. Max it will be 6. So we are just updating here 4, and we will write 6 here, and we will not move towards this side, as already we know that 2 is less than 6, so 6 will be directly put here and 4 will be directly put here. It will be minimum, so it should 4 should be present, and more than this value should not be there. So from these two value only we are directly getting to know that uh, any value exceeding 4 we will not visit. So we are just first time we are visiting this node, and we are getting this value which is greater than 4. So we will not look further, directly we will write 4 here. So here the catch is there. So alpha beta pruning is here only. You have to determine if you are encountering a value greater than this mean value, so you don't have to visit further this site, and directly you will do pruning, which you can discard this site. So 4 we will directly update here. So here the value of node B is 4. We put here. Again it will be pushed towards this side. It will backtrack towards the root node. Then again it will go towards this. Here it's uh, node C is there. It's empty. Again it will move towards this side. This side is already completed. We will visit this side, and again we will come here. We'll again move towards this. We are getting -3 here. So -3 we will push and backtrack towards node F. We will write -3 here. Then we will move towards this side. We are getting -5. So max is -3 only, between -3 and -4. So directly we will write here -3, and -3 will be pushed towards this side, towards node C. But as we already got to know that the more than 4 value is required here, max, and the value less than -3 should come here. But -3 is less than 4, So here directly we will update max value 4 here. From this only we will know that the value of alpha will be greater than value of beta. So 4 will be greater than -3. So we will not move towards this side and we will just do pruning here. We will directly put 4 here because between 4 and -3 we don't have to compare. We will directly require the max value only, which is 4, and -3 is less. So directly we will not visit here, we will stop here. And finally, what is the path we are getting from this tree after visiting the nodes and doing the pruning? Root node will be 4, and the path is optimal path is A, B, D, and I, this side. All the values are updated here is 4. So we are taking this path as the most optimal path. Now just go through this. This is the tree we are using. These are the nodes you can see from here. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. So these are the names of the nodes given in the values. After doing alpha beta pruning, we will get this. Just go through it once. And if any doubt between these two techniques, you can ask. Terminal node will be like that only. It will be present like that. It's given the values. It will be like that only. We only have to find the optimal path and the root node. What value will be present in the root node, that we have to determine. Any further question? Okay, just go this through this. I will share with you. If you have any question, then ask. If now any question left. So no any question, then we can conclude here. We'll see in the next class. I will share with you the today's notes, whatever we have learned. Okay, then we are concluding here. We'll see in the next class.